Mark Kaplan has worked in the area of quantum information for more than 15 years. He received his PhD from Université Paris Sud and worked in Montreal with Gilles Brassard, the co-inventor of quantum cryptography. Before founding VeriCloud, his research has focused on using quantum algorithms to break classical cryptographic systems and on the design of quantum-resistant alternatives. He is the CEO of VeriCloud, a company developing solutions for long-term security based on quantum technologies.
We know that in QKD, the current situation is very advanced and mature. I should update this slide because now we have a lot more of these QKD networks and some here don't exist anymore. We have 27 countries in the EU implementing at least one national testbed. So it's more than 27 test beds. We have commercial deployment in China, Singapore, Korea, so basically the Asian zone here. And we also have entanglement distribution networks, in particular in the US. So it's a rather mature field, I should say, in the sense that there are companies, we know at least 20 different companies that can work on just developing and selling quantum key distribution devices. Now, let me take a step back. I started with this slide saying this is a quantum communication protocol, and I explained to you that one instantiation was quantum key distribution. It was important to implement this protocol in order to make the technology more mature, or let's say to even just, for the sake of doing science, but it was a preliminary step before having a mature technology. And I think everybody understands perfectly this evolution, this scientific evolution. But what about what you can do beyond quantum key distribution? Even with a setup like this one, there are other tasks that we know can be implemented using QKD-like hardware, let's say. So quantum tokens, there is this work by Adrian Kent, where Alice can create tokens that come with very strong guarantees, they cannot be cloned and so on. Bob can spend the token, or receive and spend the token directly, and it offers some security that cannot be achieved classically. The digital signatures, it's a work by Walden, Kent, Dunchko, and Anderson that showed that you can use also the setup to sign messages. Quantum oblivious transfer, very interesting case. The last one showed that oblivious transfer is a resource that allows you to compute any distributed protocol without revealing your input. There was a protocol published by Bennett and Carpers in the 90s. It was wrong, but it has been fixed since then. And it turns out that we know that in theory, quantum oblivious transfer is more secure than anything that you can do classically, right? So we can have secure distributed computing in a more secure way using quantum communication networks. And then I've seen over the last couple of years, new lines of work that I found very, very interesting. If you start with QKD hardware, like standard QKD hardware, and you add things like physically unclonable functions, for example, allows you to have better authentication. If you add them these trusted execution environments, then you can have one-time programs. These are recent work that show that by augmenting these quantum networks with physical devices, you can also go beyond any security that you can obtain classically.
To watch the full presentation and over 100 other lectures on quantum technologies, training certifications and more, search Quantum Security Defense to find out more.